Hi everyone, my name is Pavlo Melnik. I am a PhD student at Computer Vision Laboratory at Linköping University. I will now present our paper, Embed Me If You Can, a geometric perceptron. We want to solve geometric problems on 3D point clouds. Planar decision surfaces, represented by standard MLPs, are not the ultimate choice for learning in the 3D Euclidean space. We argue that spheres are a more natural alternative, since the notions of distance is central in the Euclidean space. Therefore, we propose a geometric perceptron model based on spherical decision surfaces, which has an extended geometric modeling and interpretability. In our work, we focus specifically on 3D geometry, which is important for tasks such as pose estimation, which in turn is a prerequisite for grasping 3D in painting and augmented reality. Consider, for example, the 3D Tetris dataset proposed in prior work that we visualize as follows. It consists of 8 shapes comprised of 4 3D points each, which can be seen as a 4 by 3 array. But how do we feed such input to the feed-forward baseline model consisting of the hypersphere neurons, which are based on the conformal embedding of the Euclidean space? A naive approach would be to vectorize the input representing the 3D coordinates of the shapes, and then embed it in the corresponding conformal space. But this approach would cause geometric inconsistency, as 3D rigid transformations of the shapes are not equivalent to rigid transformations in R12. We strive to be consistent with the dimensionality of the input space. To achieve this, we perform the conformal embedding in a Minkowski space point-wise, and hence we obtain a generalization of the hypersphere neuron, our geometric neuron. It consists of several spheres, and each spherical decision surface classifies the corresponding point of the input shape. The unit output is then a linear combination of the scalar products. This consistency with the geometry of the input leads not only to a more intuitive decision-making process, but also to the activations becoming isometric in the Euclidean space. Although we are dealing with conformal embedding, good news is that we can implement the geometric neuron in the corresponding Euclidean space using the standard scalar product. For this, we will need to embed our Rn data vector in Rn+2. We will also represent our spheres in this Rn+2 space, using the fact that the scalar products of vectors in the conformal Minkowski space can be computed equivalently in Rn+2. But we will learn the sphere parameters as independent. In our work, we provide a graphical interpretation of the scalar product in 2D. Considering the cases when a point is either inside or outside of the learned circle, we can construct the triangles accordingly. But in either case, the scalar product of the embedded vector and the sphere determines the cathetus length. We propose a multilayer geometric perceptron model, MLGP, whose first layer consists of geometric neurons enabling the consistency with the input geometry. Similar to the baseline, deeper, higher dimensional representations are learned with hypersphere neurons. Besides our theoretical and graphical proof, we also verify empirically that the proposed geometric neuron activations are isometries in the Euclidean space. The classification experiments show that in addition to being more geometrically motivated and explainable, our modification to the baseline produces favorable quantitative results and is even superior when the input data are perturbed. The key features of the proposed geometric perceptron model are: no activation function is necessary for successful learning, due to the embedding naturally being nonlinear. Superior classification performance. Geometric interpretability. We learn spheres each classifying the respective input point in the conformal space. We also show how to properly interpret the learned spheres in the 3D Euclidean space. The computational complexity is increased typically only with a factor of 1.6 to 2 compared to MLPs. Last but not least, the isometric activations of the geometric neuron are crucial for rotational and translational equivariance. Consider checking our paper and code. Thank you.